Hi and welcome to Maths class. Today we're looking at confidence intervals, and so we're going to learn what confidence intervals are and how to calculate them. So just to give you some background about what confidence intervals are all about, we'll talk about samples. And the first thing to remember is that when we take a sample, our goal really is to find out information about the population. It's not that we want to find out what's in this sample. We use the sample in order to find out more information about the population. So then we get a sample proportion, which we call p hat, and we use that as an estimate for p, which is the population proportion. And so once I've got an estimate, I call that a point estimate. And here's an example. I take a sample of 80 adults in my local area, and I find that 18 were not born in Australia. So what that tells me then is I can calculate that p hat is 0.6, right? 18 over 30 gives me 0.6. This is a point estimate of the unknown value of p. So what I'm actually interested in is knowing what the proportion of adults in my local area is that were not born in Australia. And I use my sample as an estimate of that. But there's a problem with that. My sample is not necessarily the exact value of the population estimate. And so I can use p hat as an estimate, but it's misleading if I say that I think the population proportion is 0.6, because it's not. So p hat may or may not be a good estimate for p, and that's our problem. So what would be more accurate is if I could use p hat and then describe an interval around it which we think probably contains the true value of p. So if I go back to my previous example, if I'm reporting on this and I say, I think that p is probably 0.6, I could be quite a long way off. I don't know exactly what the value of p is, so it's not quite accurate. But on the other hand, if I said something like, I think it's likely that p is in between, for example, 0.5 and 0.7, I'm probably more likely to be saying something that's true. But how big is my boundary? That's the first question. And when I say probably, I like to be a little bit more specific than that, obviously, when I'm doing my maths. So what we're going to look for is an interval for which the probability of L being less than P being less than U is about 95%, 0.95. Now L I'm using to mean my lower boundary and U is my upper boundary. So if I had 0.5 and 0.7 as I had before, I would like to check, well, is the probability of that being true about 95%? Okay, so remember that right at the very start we talked about the fact that it's unrealistic actually to start knowing your population proportion. All the questions you've been doing so far, we know the population proportion, but in real life when you're doing research, the whole point of collecting a sample is to discover the population proportion. So now this is what we're starting on. We're starting to look at, well, what do we actually do when we don't know p and all we can actually find for sure is a sample proportion? Now, this is the formula we're going to use for our lower and upper boundaries. In this video, I'm not going to go into detail about where they come from, but I am going to look a little bit about the ingredients of this formula. So my lower boundary, I'm going to have p, and for both of them, I have p hat as my middle, and then I subtract something to get my lower boundary, and I add something to get my upper boundary. So p hat is going to sit right in the middle, just like I did before with my 0.6. I made 0.6 exactly in the middle of my 0.5 and my 0.7. So I'm subtracting k times the square root of p hat times 1 minus p hat over n, and that should look familiar to you by now. And then for my upper boundary, it's the same formula, but I'm adding that extra part. So I've just shifted that up a little bit so you can see it. The thing that I'm adding and subtracting is called the margin of error. And there will be questions when you're actually just asked to calculate the margin of error. This is the formula that you need. K times p hat times 1 minus p hat over n, or the square root of all of that. Okay. Now, that part there, when I said it should look familiar, that's because it is a standard deviation formula for your sample, but instead of using P, which we've used previously, now we're accepting, well, we don't know P. All that we know is P hat, so let's use that as an estimate. So we put P hat into that formula as an approximation for P. Oh, I need to shift this up a little bit. So what we want is K. Oh yeah, so that's the other thing I haven't talked about in this formula is K, which is just here. Oops, what did I do? I went back. Here we go. K is just there, all right? So we want K such that we get approximately 95% chance that my actual p-value falls within these boundaries. That's our goal. We want to work out what my margin of error is such that I can be confident to within 95% that the boundaries I'm giving you actually contain the real value of P. Now, I'll give you a little bit of background of how we get to that. So this leads us to this formula here. The probability of P hat minus K times the square root of P hat times 1 minus P hat over N is less than P hat plus K and the square root. Okay. So, oops, why did that move? This is very closely related to this. So we've got this probability here, and now I've written down this probability that negative K is less than Z is less than K. If I showed you the derivation, you would see that actually when I transform this, it turns into that. Okay, so what I'm looking at now is my Z curve. So basically, here's my Z curve. And this is 2.5% at this end. And this is 2.5% at this end, which means I've got 95% in the middle. That's 0, okay? So this is K, and this is negative K. All right, that's a familiar problem to us. We can solve that using our CAS. So I'm going to do that now. I'll just pause while I bring up my CAS. Okay, so there's my CAS calculator. And what I'm going to do, so I want to calculate an inverse. So I'm going to distribution, I'm going to inverse, and I want inverse normal CDF because this is a normal curve. And I'm looking for a center tail because I had symmetry on either side. I had negative K and K. So I'm looking at a center tail, and I want the probability to be 0.95 that my values fall in the middle. Okay. And I get negative 0.96 if I go to 2 decimal places. Now that's the first value, and then by symmetry I know that the second value is 1.96. So it's giving me the two values on the curve, negative 1.96 and 1.96. So this gives me a value of K is 1.96, and that's how we get to that. So let's just hide that again. There we go. Okay. All right, so this is a summary. For a confidence interval of 95%, this is our formula, right? This is my interval, so it's written in interval notation. I've got curved brackets, but of course it really makes no difference. As you know, less than or equal to or less than for a normal curve makes no difference. And then noting that this particular part is my margin of error. So I've just changed the formula and I've replaced K here with 1.96, which is the value that I got earlier. All right, now we're going to do some worked examples. So if I take a sample of 80 adults in my local area and I find that 80 were not born in Australia, I need to find a 95% confidence interval for the population proportion P. So the first thing I'm going to work out is what was P hat from my sample. And P hat, I have 18 out of a sample of 30, which gives me 0.6. Okay. I'm looking for a 95% confidence interval, which means I'm going to use a K value of 1.96. And so my interval is going to be P hat minus 1.96 times the square root of 0.6, that's P hat, times 0.4, that's 1 minus P hat, over 30, that's N, and of course then P hat plus the same values. I'm going to put that into my CAS. Let's pull up CAS again. Where have you gone, my friend? There he is. Okay. I'm doing this, I'm not doing any special, hang on, maybe I can move that CAS over so I can see those numbers. Yes, that helps. I'm not doing anything special here other than just entering things into my calculator. Oh, I didn't write the value of P hat. I'll fix that in a moment. So I'm going, P hat was 0.6 minus 1.96 times the square root. I need my keyboard. And I've got 0.6 times 0.4. And of course I've got those asterisks instead of the times because I'm on my keyboard rather than my handheld. And that's 30. And hit enter. All right, so my first value I have 0.4247 if I go to 4 decimal places. Okay, and when I want to add it, I just go back into CAS and I change that subtraction to a plus instead of typing the whole thing again. And I get 0.7753. Okay, and that's my interval. Now, it's worth noticing that this is quite wide. So remember I used as an example earlier that I might go from 0.5 to 0.7. In fact, I can be 95% confident that P is between 0.4247 and 0.7753. It's quite wide. It's not very specific. And part of the problem here is my sample size. I've only taken a sample of 30 adults. So I want you to notice that in my formula, the sample size is on the denominator of the part that I add and subtract, and it's square rooted on the denominator. So the actual value on the denominator is much smaller than 30. It's less than 6, right? Because the square root of 36 is 6. So it's between 5 and 6 is what I'm dividing by. So if I want to narrow that interval, what I need to do is increase my sample size. So what we'll do now is the same question, but now I've changed my sample to 400 adults. Okay, so I have found that the sample proportion, the proportion who were not born in Australia, is 0.6, which is the same as in the last question. P hat equals 0.6. I need to find a 95% confidence interval. So that's going to be 0.6 minus 1.96 doesn't change. The 0.6 times the 0.4 doesn't change. The only thing that changes here is 400 on that denominator, and then 0.6 plus the same numbers. And this will still be in my CAS, which will make it quick. So let's look at CAS. Oh, I've just realized you're still seeing CAS. Sorry, you can't see what I've got there. There. Okay, so that's what I've written. And now let's put those values into my CAS. All I need to do here, I'll do my subtraction first, and then I change that 30 to 400 for my lower boundary. I get 0.55199, 0.5520. You can't see that, I'll show you in a moment. Oops, I'm moving the wrong thing. Put it over here, there we go. 0.5520 if I round that off, because the 9 rounds the next value up to 2. And now I'm just going to do that again, but changing that to plus. Oops. And I get 0.6480. Okay, so I've narrowed my interval a little bit. You'll notice that the 0.6 is still right in the middle, but now neither 0.5 nor 0.7 are actually included in my interval. So as I increase my sample size, I can narrow that interval. Okay, now, what if I don't know what sample size to choose, but I'm aiming for a particular margin of error? So what that means is I want my margin of error to be 2%. So I want this part to be 2%. Okay, so that means in this example, same question, I've got 1.96 for K, 0.6 times, 0.4. But now I'm dividing by N. N is unknown. Okay, so this is going to give me a 2% margin of error because I've made that equal 2%. All right, so let's do it. Let's just rearrange this. And I end up with, on the right-hand side, 0.02 over 1.96. And then I have to square both sides. That's going to give me 0.6 times 0.4 over n. And now I'm going to flip both sides and multiply through, and I get n is 1.96 over 0.02 squared times 0.6 times 0.4. Put it into my CAS again. You don't need to see me do that. Okay, so you can see there that my CAS has given me an answer of 2,304.96. I'm going to round that up to 2,305 because if I go to 2,304, I'm under my cutoff. So I'll just hide that again so you can see, and I'll write my answer down. 2,304.96, and so 2,304 is going to be my sample. Okay, there's just one more thing to look at when we think about confidence intervals. I talked earlier about how increasing the sample size can decrease my margin. Decrease the size of the intervals. It can narrow it. So, in fact, I can choose, I've been talking so far about 95% confidence intervals, but we don't always have to choose a 95% confidence interval. What we do always have to state is what we chose. So if I was doing research and publishing my results, I wouldn't just publish the confidence interval, I would say it's a 95% confidence interval. So the K value is what changes, and I would use my CAS to calculate them in the same way, but I'm not going to do that now. But if I need a different confidence interval, then I'm simply going to use a different value for K in this formula. So this is the general formula, whereas I use 1.96 for most questions, because most questions are going to ask me about 95% confidence intervals. But I do need to know that if it's a 90% confidence interval, I'm going to use 1.65, and if it's a 99% confidence interval, I'm going to use 2.58. Now, I hope you can see that if I multiply the square root part by these different values, k is around about 2. It's nearly 2. So I'm approximately doubling this number here, whatever that number is. Okay. If I multiply by 1.65, I'm much less than doubling it. If I multiply it by 2.58, I'm multiplying it by more than 2. So what that means is that what I'm going to get is going to look something like this. Here's going to be my 90% confidence interval. It's going to be nice and narrow. Here's going to be my 95% confidence interval. And my 99% confidence interval is going to be wider again. This is the 99% confidence interval. So it's a choice that you make as a researcher. Do you want to give a higher degree of certainty that this interval contains P, but then it's going to be a very wide band and maybe not so useful, right? It's not very useful to know that the proportion of people born outside of Australia is somewhere between 0.1 and 0.9. It doesn't tell us much. We're highly confident that P is somewhere in that value, but not very informative. On the other hand, if we go for our 90% interval, we get a narrower band, but less confidence that P is actually in this interval. So if I say, and I'm just making these numbers up, my value is between 0.59 and 0.61, but if there's a 10% chance that P is not in that value, then I'm not being very specific. So that's a reason why 95% is often chosen. It's a good balance between getting our interval width not too wide, but at the same time having a high degree of confidence that this actually contains our p-value. Right, that is the end of this video on confidence intervals.